Hello, and welcome to part 7 of this webinar series on model-based design for DO178C software development. My name is Mike Anthony. I'm an application engineer with MathWorks. The topic for this particular webinar is conformance to coding standard and proving correctness, and that's proving correctness of the code. So really the tool that we're going to focus on in this webinar is polyspace. All right? So if we refer back to the workflow diagram that we've been following for the entire series, you can see that polyspace shows up in a couple different places. So the first, which is the next step in the series, would be this idea of the source code conforming to coding standards. And so we'll look at how polyspace can help you with that, specifically by using the MISRA-C coding standards. Now, polyspace also shows up in the step of verification of the object code against the model here, and verification of the object code against the requirements here. And I'll talk about why that's the case. And this is related to the other aspect of polyspace. So part of polyspace is it has static analysis capability. And so part of that static analysis is static rules checking. And so that's this part about checking your code against coding rules. The other part is this more formal verification of proving the absence of runtime errors. And it's in proving the absence of runtime errors and also in how polyspace does that formal analysis that actually allows you to take credit for some of these verification activities. And so we'll actually talk about both, even though these are not necessarily related to this sequential step in the process. While we're talking about polyspace, we'll cover all of these topics. So jumping into the tools, you'll see we're still using exactly the same model that we've been working with. The one thing that I want to point out is if you recall from watching part 5 of the webinar series, which was all about using Simulink Design Verifier and formal analysis to do verification of the model against requirements. So in that part of the webinar series, we looked at using Simulink Design Verifiers detecting design errors and how part of what that found was that we needed to include additional documentation in our model specific to the expected ranges of our root level inputs. And you can see that I have taken those out, the ranges that we put in as part of that activity of using Simulink Design Verifier. And the reason for that is we'll actually see that polyspace will give us back that exact same information by doing analysis on the code. And so we'll take a look at that and how these ranges are related to possible overflows and runtime errors as we go through kind of the polyspace example. All right. So the first thing we need to do, we have the model, so we need to generate code. So I'm going to hit Control B, all right, and then you'll see down here in the command prompt that we're actually generating code. So this is exactly the same code that we were getting as we went through the exercise of code generation and traceability, so on and so forth, okay? So assuming that we have generated code, the next step is to run the polyspace verification. Now, polyspace has the polyspace link for SL, which is a built-in link for Simulink. So if you have polyspace and you have this link, then you can see under the code menu in our Simulink model, we have this menu item for polyspace. And this is basically just a way from within Simulink that we can manage what we want to do as far as code verification with polyspace. All right. So the first thing we want to look at is our options, just to see what kind of options we have. And you can see that now the options are included in the same kind of configuration parameters window that all the other MathWorks options are. So we've been working very hard at kind of integrating polyspace into the MathWorks tools to make it a more consistent user experience. So within these options, we can go through these really quick. So the first is verification settings and you have the choice. So you can do your own custom project configuration, which is what we're going to do just so we can look at what that means. Or we have a couple preset configurations. So this would be some customizations, but turning on the MISRA AC AGC rules. So this is a set of MISRA rules that was specifically developed for automatically generated code. It has become a very popular coding standard for automatically generated code throughout many industries, automotive, aerospace, and a couple of others. All right. We have another built-in, so these are just kind of pre-customized configuration sets, if you will. This one does your standard MISRA rules. And then these last two don't do formal verification, they just do the static rules checking. All right. But we're going to use our own custom one. And if you want to look at that custom configuration, you hit this button here, configure. And this will open up polyspace, and we can actually edit the configuration in the polyspace project configuration editor. All right. So if I make this window a little bit bigger so we can see what's going on. So in here, this is basically our polyspace configuration file. All right, and you can see that we can customize a lot of stuff. All right, so we can kind of tell polyspace which target and compiler we're using. Now, it's important to note that polyspace, it is static analysis or static verification. In other words, we don't compile and execute the code in order to do the verification that polyspace does. However, part of the verification is we do check to make sure that the code actually will compile. So even though we don't actually execute it after compiling it, we do check to make sure that the code will successfully build and compile. All right, and so that's why you can kind of customize your target and compilers and so on and so forth. All right. The coding rules and code metrics. So again, this is where you can turn on and off whether you want to do static rules checking. All right. So in this case, I'm going to turn on the MISRA AC AGC rules. All right. I want to include these. And then even within here, you can see there's a couple different options. So the way the MISRA standards are written, there's kind of these obligatory rules, and then there's also recommended rules. And then, there's some subsets. So this is one of those things where, especially if you might have your own project-specific or company-specific coding standard, oftentimes those specific coding standards can actually be recast as some subset of the MISRA rules. And so in that case, you might want to use kind of this custom set of rules. And then you can go in and actually select exactly which individual checks you would want to perform. All right. I'm going to just stick to the obligatory rules. Okay. The other thing, and this is actually a relatively new feature of polyspace, is similar to what we could do with the model advisor. And recall that we talked in depth about the model advisor in part 3 of this webinar series. And I mentioned that one of the key aspects of having Simulink verification and validation is that it gives you the capability to write your own custom model advisor rules. All right. Well, this capability within polyspace is exactly the same. So now, if for some reason your project-specific coding standard can't be fully expressed as some subset of the MISRA rules, you can actually write your own custom rules, and then polyspace will apply those custom rules as it does its static rules checking. All right, so that's what this is all about. I don't have any of those written, so we're going to turn that off. The next subsection here is this verification mode. And again, this gets into a similar conversation to the one that we covered when we were talking about Simulink Design Verifier. And that is that when you use polyspace, you have to make some fundamental decisions about what level within your, say, software architecture you would want to start doing this kind of analysis. We typically don't recommend, especially for larger and more complicated projects, that you wait until the very end and then run polyspace on the entire application. Starting at that point, it's very likely that, one, it's going to take a long time to do the analysis because this is using formal methods. Specifically, the one that polyspace implements is called abstract interpretation. But if you wait until you have like a couple 100,000 lines of code or something like that, running polyspace on that entire application, though eventually it will run, it's going to take a really, really long time. And then more than just the time it will take to actually run the verification, it's going to take a long time for the user to actually interpret and understand all the results that we would provide. So we often recommend that it's better to start by kind of verifying some subset of that capability, which we call a module. All right, and so here's where you can kind of specify that, if you will. Now, I am actually making that specification by running this on the generated code just from this one particular model reference that we've been working with, the logic controller. Say, as opposed to running polyspace on the code that comes out of the logic controller and the image processing algorithm and the closed loop motor controller, et cetera, et cetera. All right, so I'm actually doing this kind of component verification by running it through the Simulink link product on just this one particular referenced model. All right. The next section here is verification assumptions. So again, this is where you can tell polyspace if there's some things that you want it to ignore. Again, this is very similar to Simulink Design Verifier and just picking the assumptions that you want to make with respect to the formal analysis that we're going to perform. All right. The next section is on precision. So there's a couple different precision levels that you can choose. There's 4 of them, 0 through 3. All right, so I'm going to stick with level 2. So that's the precision level, which is different than the verification level. So the verification level is more about kind of how difficult or how robust we need the check to be. And so in this case, since we are talking about, say, a DO178C example level A process, I want to set this to be level 4, which is the most rigorous. All right. The next choice is this post verification. There's some capability within Polyspace that we call the automatic orange tester. We'll see what orange means. For now, I'm going to leave that off until we kind of talk about what the results are that Polyspace provides. And then, of course, in keeping with that same recurring theme throughout this entire webinar series, Polyspace has the ability to do automatic report generation. And so you can see I can say generate a report. There's a couple different built-in reports that we can develop. So there's one which is coding rules. So this just reports on, in this example, did the generated code from the model conform to the MISRA AC AGC guidelines. All right. The developer reports include the static verification for proving the absence of runtime errors. Okay, and so the intent of these reports is if you are doing the runtime error checking, these are good reports to kind of put out to show that you successfully did that. All right. So we'll actually look at these reports in a little bit. All right. So once I have this, I can save this. And you can see that in this case, it's saved in this file logic_controller_config.cfg. All right. So once I have that saved, I actually want to turn the report generation off because we'll look at that at the end. So once I have that saved, now I want to actually go and start the analysis. All right, so let me close our configuration parameters window. And again, under code, we can go down to Polyspace. There's this option Polyspace for embedded coder, and you can see we can verify the generated code. All right, so that's what I'm going to do. And if we look in the command window, you'll actually see this verification start. All right, now we already generated the code. Part of the link is that it knows the assumptions that embedded coder makes as far as where it puts all of the different files that are necessary for Polyspace to do the verification. So in this case, it knows that the code will exist in from this directory that we're currently in. There will be a directory called ERT_RTW. So logic_controller_ERT_RTW, and in there is where all of the automatically generated code actually goes. So it knows to look in there for all the .c and .h files, and then you can see it's actually going through and running the analysis. Now you have a lot of options as far as how you can have Polyspace work with the rest with MATLAB and Simulink. In this case, since the amount of code that we're verifying is very small, I'm actually doing it, and you can see it's built in, and I'm watching the output right from within the MATLAB command prompt. So that's one option. For larger problems, you're probably not going to want to tie up your MATLAB workspace doing this. And so this is where you get into the different licensing options of Polyspace. So fundamentally, Polyspace has a client and it has a server. And the intent of the server is that it's basically a dedicated machine where you can offload kind of very intense verifications to that dedicated machine, which is there to do the analysis, because the analysis can be very computationally intensive, and that frees us up on our workstation to kind of do other work. So you can decide whether you want to do the verifications locally or do them on the server. It's all based on how big and complex the code that you're attempting to verify really is. All right. So you can see that the verification has completed. All right. And so now we want to look at the results. And so again, we can go under code, Polyspace, and I can say open the results for this generated code. And this will open up the Polyspace results viewer, and we'll actually get to take a look and see what happened. Now, there's, again, a couple different things. We're going to look, one, at the static analysis results, so the static rules checking, and then we're going to look at the runtime error verification. All right, so there's a couple different things that we probably want to look at within the results viewer. So let me make this a little bit bigger. So the first thing you'll see is there's these different methodologies. So there's methodology for C, methodology for C++, methodology for model-based design. All right, so basically this just looks at the different kinds of checks that Polyspace can determine. All right, so we're going to do methodology for model-based design. All right, and then down here in this lower left pane, you can see that we can view in the Results Explorer all checks, coding rule violations, and runtime checks. All right, so let's start with coding rule violations. So you can see that this ran our automatically generated code against the MISR coding rules. All right, and you can see that it found one coding rule violation. All right, and so we can kind of navigate down through the call tree here and get to the actual violation. All right, and you can see that it then illustrates where the violation happens in the generated code, which is here in this divide operator. All right, and then up here in the check details, it tells us exactly why it's saying that this is a rule violation. All right, and so the specific rule in question here is Rule 10.2, and it says implicit conversion of the binary divide right-hand operand from double to float that is not wider than a floating type, or implicit conversion of the binary divide left-hand operand from float to double, but it is a complex expression. All right. So in other words, what this is saying is we're somewhere in here we have a double precision divide. All right, but you can see that we have also declared some things as singles. So what's happening here is in this statement we have a mix of singles or float 32s and doubles float 64s. All right, so if we look at the typecasting, you can see here this real 32T, so that's this angle scaling is a single. All right, but this angle scaling here, this real T, this indicates a double. All right, and so the rule that we're violating basically says you can't be mixing these data types, because then we're doing a cast down to a single, and it's possible that we could be losing precision. All right. So of course this begs the question, well, where is this in the model? All right. And the nice thing is that the Polyspace link allows us to navigate back to the model using the traceability that we discussed in the previous webinar that's built into Embedded Coder. All right. So you can see that we can just click on this divide and it'll bring us back into our Simulink model and highlight the appropriate block. All right. And sure enough, you can see that here in this divide block we have a single, and it actually looks like for some reason up here we have a fixed point, and that's because this is coming in as an integer. All right, and so essentially what's going on here is we're doing some internally, Simulink is doing some typecasting for us in order to get this operation to work, so that we can actually divide a float 32 by basically something that was coming in as an int16. All right, and I would actually say that that's not a very good idea. I, in general, tend to not like allowing the tools to make decisions like that for me. All right, so we have a couple different options as far as how we might want to handle this. So one, instead of bringing this in as an int16, we could bring this in as a single, and that would actually propagate the single data type all the way through here, and we'd be fine. The other thing is we could decide that maybe we don't want to do that, and we could maybe just put it here. In this case, it actually doesn't make that much difference. Rather than change the actual root level import, which would mean I'd have to go back and change my ICD, and then I would have to do some sort of verification about that, I'm going to just make the change internally to here. All right, so what I'm going to do is just go grab from our signal attributes library a data type conversion block. All right, so let me just make this a little bit smaller. So I'm going to hide the name, and if I double click on this, I'm going to say output data type. I'm going to make it a single. All right, and then I'll hit OK, and then I'm going to just drop this right before this 1/2. All right, so given that change, what I want to do is actually now regenerate my code, because I've changed it. So I got to save my model, and then I'm going to regenerate my code. And before I do that, I'm going to close the results viewer. So I'm actually going to do Control B again and regenerate my code. And you can see down here in the workspace, it's regenerating. And then once that's done, we could go find that particular line of code if we wanted to look at it, but I'm going to just run my Polyspace analysis again. All right. And so again, you can see it's running this as a local verification, which again, it doesn't take too long because in this case, the generated code isn't that large or complicated. So we can just wait for it to happen. And then what we'll want to do is look at the results again and understand if that change in the model basically prevented that MISRA rule violation that we found previously. All right. So you can see the verification is done. So let's go look at the results again. All right, and again, I'm going to turn this to methodology for model-based design. And then let's just look at the coding rule violations. And you can see that now I have none. All right. Now, I don't remember off the top of my head what line that error was on. So what I'm going to do is actually come to my model. I know it was related to this divide block. So I'm going to use the model to code traceability that we get from embedded coder. And I'm going to go find it. So that functional line of code was essentially here on line 147. So then if I go back into my polyspace results viewer, I can go down to line 147, which is here. All right, and you can see that it was this divide, and now we're not violating the MISRA rule on that divide. All right, so that's the MISRA rules. Now, the other thing, of course, to look at is the runtime checks. All right, and I'll just turn all checks on, so that includes the runtime checks. So this gets into kind of I think, the real meat of what polyspace does, which is proving the absence of runtime errors in code. Right? And again, it doesn't matter whether it's automatically generated code, like it is in this particular example, or whether this is handwritten code. Polyspace can actually run on generated code or handwritten code. It doesn't make any difference. Okay. In this case, we're running on the generated code. And so what polyspace does is it proves the absence of runtime errors. So if you're familiar with kind of embedded software development, runtime errors are these really nasty software errors that are very difficult to find through testing. Right? So they're things like indexing arrays out of bounds, pointers out of bounds, divide by zeros, data type overflows, so on and so forth. All right. So you can see that in this case, polyspace has given me 4 oranges. So the way polyspace reports on runtime errors is it basically colors every operator in the code. So red means that every time that operator executes, you're going to get a runtime error. Right? Gray means that the code is theoretically or mathematically unreachable. Okay, so again, this is very, very similar to that dead logic detection that we went over with Simulink Design Verifier in one of the previous webinars. Right? Orange means that there are some cases for which a particular operator could exhibit a runtime error, but there are also some cases for which that particular operator is safe. All right, so that's orange. And when you get an orange, then you need to understand what is the scenario for which that operator is unsafe, and then basically defend against that. All right, and so we'll see how to do that in a second. And then green. Green is the final possible outcome. And green means that no matter how you call that operator, it is safe. There is no possible way that that operator could ever exhibit a runtime error. All right. So since we don't have any reds, let's start with our oranges. So again, if I kind of navigate down through the call tree here, you'll see the first orange is an overflow. All right. And so we're kind of back on the same line of code that we've been working on. All right. So if we read the error, it says operator divide on float may overflow. All right. Result strictly greater than max float 32. All right. So basically what this is saying is that when we do this divide, there's a chance that we could overflow the single precision, so the float 32 data type. All right. And you'll actually see that this multiply in the same line, which is actually here, is giving us the same error. And you'll also see that we're getting an orange on the divide not just because of overflows, but also because of a potential divide by 0. All right. So again, let's go back to the model and see if we can kind of understand why polyspace is saying this. All right. So recall that I said from the beginning that I do not have any documentation of the range of this particular variable image width. All right. And so without documenting that range, polyspace assumes that in this case it's full range of an int 16. Okay. And so being full range of an int 16, right, when we get to here, it's a potential divide by 0 because it's possible there is a situation where that input could be 0, right? In which case this would be a divide by 0. And if this is divide by 0, then clearly the outcome of this would also overflow the single precision data type because the result would be essentially infinity, okay? And so that's what's going on here. And so what we have to decide is how do we want to fix this, right? Basically what polyspace has indicated is that this variable input, image width, being full range is potentially going to cause a runtime error in the code. Again, there's a lot of cases where this is a safe operator, but there are some cases where this is an unsafe operator. All right, and so the decision comes, well, how do we fix this? And of course, we don't ever edit the generated code by hand. We have to make the change in the model. All right, and so there's really two different ways that we can fix this in the model. All right, the first is using the same technique that we used when we were using Simulink Design Verifier, which is to actually come into here and document our ranges. All right, and again, in this particular case, we actually know that the width of the image that we're getting in here is constant within the execution of our software project and is 320 pixels because that's the built-in width of the image that the webcam is capturing. So we can actually set this to be 320 for both its min and its max. All right. And while we're in here, we probably ought to constrain this one too. All right. So recall that this is the ball position. So -1 actually indicates that the ball is out of the field of view. And then again, the maximum position this could be would be 320 because that's how many pixels are in the image. All right. So this can vary from -1 to 320. All right. So if I, again, document these ranges in the model, then polyspace will actually pick up on that documentation. All right. So once I've documented these, again, I don't have to regenerate code because recall, anytime I put information into these min and max fields, it's just for documentation. All right. Embedded Coder doesn't do anything with those. All right. So it's, again, at your own risk. If you put the wrong thing in here for documentation, and then you do some sort of analysis that depends on these, like running Simulink Design Verifier or running polyspace, it's possible that you could be covering up a real error. So you have to be very careful when you document things like this. All right. Now, if we do that, again, we don't have to generate code, again, because this documenting those doesn't change the generated code at all, but we do have to rerun our verification. And if we rerun our verification, what we'll see is, again, polyspace will pick up on those ranges that we document through a specific file called the data range specification file, or DRS file. All right. And so we can take a look at that and see exactly what that looks like. But essentially what this is going to do is rerun the polyspace verification, but now polyspace is no longer going to make that conservative assumption that image width is full range of its data type. It's going to constrain it to the min and max that we documented. All right. And so again, this is all defined in this file, the data range specification file. All right. And so you can see that when we documented those ranges, polyspace picked up on what we put into the Simulink model. All right. And so given those ranges, we reran the verification. So now if we go back and look at the results, hopefully what we'll see is with those assumptions that constrain the verification that we're trying to perform, right, we no longer get any oranges. And so again, if we go back to that same line of code, which was still line 147, right, you can see that now it's telling us that these operators, this divide, there's no longer a potential divide by 0. So the way this is actually implemented, if we look at this divide, right, what it's actually doing is it's doing kind of an inverse of the input to the top part of the block, right? So this is image width divided by 2, which actually happens here. So it's doing 1 over that and then multiplying it by the bottom part here. All right, so the difference between ball position and the total width of the image. All right, so by constraining that root level import in the model, we've made sure, guaranteed, that there's no possible way that we could ever overflow or get a divide by 0 on this particular operator. All right. So again, that's one way that we could fix that. But that makes an assumption, right, which is that we know for absolute certain that these ranges that we documented are correct. And so if you are absolutely 100% certain that these ranges are correct, then this is a perfectly valid way to do this, all right? But again, it's not as robust, right? The more robust verification is, let's say we don't know these for sure, right? Then again, you can actually allow this to vary, right? And that way Polyspace is looking at kind of the worst case scenario, if you will. And that's how we got the orange in the first place. So the other way that we could fix that orange is, instead of this documentation, we could actually add protective code, all right? Or in this case, protective modeling, all right? And so the way you do that in the model would be to actually go grab a saturation block. So let me put these back to full range, just so we can make sure that this actually works. All right, and then what I would want to do, and again, you could choose whether you want to do it here or whether I want to do it after. I'm going to do it right after I cast it. So I go into the Simulink library browser, and then under discontinuities, I'm going to grab a saturation, right? And then in here, I can say something like 320, 320. Okay, and so what this does is that it basically protects you from any possible scenario by inserting effectively protective code to say that coming out of here, this has to be within the range we expect, the range we expect actually being just a single constant of 320. All right. Now, in this case, since we did make a change to the model, we do actually need to regenerate our code. So I'm going to save, and then I'm going to build again. And so now we'll actually have different code. All right, so we need to regenerate the code. And we can actually see, so again, let's use the traceability. So let's navigate to our code. You can see that we've actually created new code that didn't exist before because of that saturation block. All right, so now the idea is that we have to, again, run our Polyspace verification. Because the code actually changed, we need to rerun our verification. And what we're hoping to see is that this will also effectively prevent those potential runtime errors of divide by zero and data type overflow. All right, so once the verification is complete, we can open up the results again and take a look. All right, so if I go back to code, Polyspace, open results. So again, you'll see that we don't have any potential runtime errors. And if we, again, go back to kind of that same line of code, right, which is here, you can see that it's still saying that this is safe. And this is safe because this temporary variable here, RTB underscore dead zone, you can see in here, this is essentially that saturation block. All right, and so we've, in the code, actually constrained it so that that can only ever have the value of 320. All right, and so that again makes this divide safe in all possibilities. All right, so this is another way to basically turn those oranges into green. So there was two. There was one, we just documented the ranges, or we could add protective code or protective modeling. All right, now the choice of which one of those two options is correct is, again, dependent on the level at which you did the verification. All right, so we chose to do this verification just on logic controller. All right, if I had, say, done this verification on the entire system level model, all right, so let me open the system level model real quick. So we did the verification just on this component. If I had done the verification on this component and this component linked together, then we wouldn't have had that runtime error, those oranges, in the first place, because Polyspace would have found that mathematically inside of the image processing algorithms, the output image width could only ever have one value of 320. All right. So I would actually contend that in this particular case, it's smart to start doing the verification on smaller components, but it's important to recognize that when we do verification on the smaller components, it's a really good idea to know your interface definitions, especially ranges, so we can constrain that verification. So in this particular instance, I would actually say that documenting the ranges in here is the better option. And the reason for that is because when we add protective modeling, right, that solved the problem on this scale, but the reality is that when we integrate this code, say with the code from that image processing algorithm, you're actually creating dead code because we're, in this saturation block, we're protecting against this value going over 320 or under 320. And that's actually going to create logic in the code that we saw here, right, which you'd actually never be able to access these logical paths in the code, right? This statement could never ever go true. And so if you just go start adding protective code or protective modeling everywhere, you're actually going to create a situation where you're causing dead code or unreachable paths in your code because you're doing extraneous error checking. So not only is this unnecessary, this slows down our code, and it actually creates a situation where we're going to be unable to cover all of our code. So just adding protective code is not always the answer, all right? In this case, because we know those ranges really are correct, that would be the better way to fix the potential errors in this particular instance, all right? However, if you're in an instance where you don't know and you really do need to assume that that variable could be full range coming in, that's where adding protective modeling constructs or protective code is the better way to go. All right. So assuming I go back to the model where we fix this by documenting our ranges properly, if we looked at the reports, again, there's a couple different reports. So there's the coding rules report. And so this is just a nice paper document to show that you were successfully able to follow all of the MISR rules. And again, which MISR rules you want to follow, you can choose in that configuration set. So we looked at that, all right? But this report is the one that you would really need to have as your data artifact to show that your code conforms to coding standards, okay? Now, the other thing that's important to note is that polyspace is also part of our DO qualification kit, all right? And so that's very important here because when we generate this rules report and show that the code conforms to a coding standard, because polyspace can be qualified, there's no need to review the code for conformance to standards or review the output of this report. So again, this is a big time saver when you start to think about tool qualification, and the fact that every time you change the code, you typically have to manually review that code for against coding standards. So having polyspace be a qualified tool in your process, you can leverage this report to exempt you from having to do that particular manual review of the code. All right. Now, the other thing, again, that polyspace can do, if you qualify it, is we saw that when we ran the polyspace analysis, it figures out the mathematically possible range of every variable at every operator. And given that information, you can actually use that information to know what the theoretically or mathematically possible range of every variable is. And if you think about what that means, we have a formal proof then of what every variable's possible range could be. And this is the kind of information that you would otherwise try to get by doing boundary value testing. And so another nice side effect of what you can do with polyspace is you can actually use the results from polyspace to exempt you from having to do some of your other traditional downstream boundary value testing, because we've formally shown what the mathematically possible range of all outputs for given input considerations is. All right. And so because you can use the runtime error results of polyspace to exempt you from some of that downstream testing, that's why we include it in these verification steps of the object code, all right? Because it can actually exempt you from having to do boundary value testing later on. The other thing that's worth noting is because polyspace is a tool that can prevent you from having to do downstream testing, in DO178C and DO331, polyspace is actually considered a criteria 2 tool, all right? And so our qual kit, the DO qualification kit, is already all set up to give you all the documentation and test cases you need to be able to qualify polyspace as a criteria 2 tool in your development environment. All right. So then really quick, again, we can look at, say, the other report. So this is the developer report, and basically this includes the MISRA checks, but it also includes information on all the runtime error checkings. All right. And so this is, again, a useful document to show exactly what verification we ran and show that all of your code doesn't have any potential runtime errors in it. So that's basically it for polyspace. So again, we showed how we can use polyspace on the generating code. We looked at the polyspace link for Simulink and how that kind of integrates polyspace in with the Simulink environment. And we also looked at how you can use polyspace, one, for static rules checking. So we compared our generated code against the MISRA AC AGC guidelines. We actually found a potential rule violation. We used the traceability aspects of embedded coder to go back to the model and make the appropriate fix in the model to prevent that rule violation. We then ran polyspace's runtime error verification, so the formal verification, and we found that we had potential runtime errors, a divide by zero and a data type overflow, and we needed to make some alterations to our model to basically prevent those potential runtime errors. And we did that in two ways. One was by documenting the ranges, which we can actually do because we understand the interface to the component under test very well. The other option is if you're in a situation where you don't really understand your interface ranges, then you can effectively add protective code or protective modeling constructs to actually physically prevent in the execution of the software any potential runtime errors. All right. So that's polyspace. Polyspace is covered as a criteria 2 tool in the DO qualification kit. And the other thing that's worth noting about polyspace is, again, just because in this example we ran it on generated code, polyspace can actually be run on generated code or handwritten code. So the other really nice thing about polyspace is, again, in a DO 178C type environment, you could run polyspace on all of the handwritten code that you're likely to integrate your generated code with too. So things like device drivers and so on and so forth. So polyspace can actually help you with the DO 178C verification requirements for your handwritten code, as well as for your generated code that in this case is part of the overall workflow that we're going through. So that's it on polyspace. The next section is going to be about Simulink Code Inspector, which is, again, another type of verification that we can do at the source code level. So if you're interested, please watch the next one. Otherwise, thank you very much.